dreaded ISO 15189. So at the moment, all the labs in the UK are migrating over from the former standards that had been in place for, updated regularly, but been in place for like ever, to these new international standards. So ISOs are the kind of things you have if you run a manufacturing company to prove that your method is manufacturing the same thing over and over and over and over again. Works okay for numbers. So those of you who are HEME or Clean Chem orientated, your data is a number. It's quite easy to at least give validity to a number. For microbiology, proof is a lot more complex. And then I started thinking, what sort of microbiology? Because not all of you are NHS related. Not all of you are going to go there. Some of you are going to want to go and do PhDs. How do you prove anything in microbiological research either? And so actually, what I've done is put a little bit of both in. So there's some aspects of it that will be proof in a clinical setting, and some aspects of it that will be proof in the research setting. And they are quite different, although they do overlap. And so I'm going to show you some. I've dug out my postdoc science. I knew it would come in handy one day because I've never got a publication from it. But we're going to use it today to look at some difficulties around proving anything in microbiology. And then obviously by the end of the series of lectures on proof, hopefully you'll come to a bit of a picture about whether we can ever prove anything in science. Okay, so we're going to have a little bit of a look, and I will, as I said, comment back to epidemiological proof. So the concept of trying to prove what the meaning of your data is in microbiology really does depend on what that data is. Is it numerical? Now there are times when even microbiologists run a machine that gives you a number. Not that often, but it does happen. And certainly in research it happens more than it does in clinical settings probably. So we'll see some number-based stuff. But also, are you talking about a single time point or over a time course? Because a lot of stuff we do in microbiology, if you do a single time point, how valid is that? And we'll look at some classical examples of where a time point versus single time point is it. And then there's kind of a technical natural balance. We do a lot of things, and Ian probably will have touched on this last week. There are methods you can do quite easily and get loads and loads of replicates. Yeah, if you quantify your RNA really accurately and then run 20 parallel aliquots of that, you should get the same result 20 times. But some of the methods that we use, both in molecular, and Ian may have mentioned one of them, in which case it will overlap to him, but some of the methods we use, doing replicates is actually difficult. And these bacteria, you might have already seen it from practical classes, they don't read the rule book. They don't go, I must be ready by 9 o'clock tomorrow morning so that so-and-so can run their experiment. They have this horrible habit of misbehaving. I had it this morning when my project student in the lab came in, wanted to do growth curves on Haemophilus influenzae. I looked at the broth that had been up over the weekend and went, that probably ain't Haemophilus influenzae. So I just went, that looks wrong. When she grammed it, lo and behold, it was a gram-positive coccus, and something had gone wrong overnight or over the weekend. So they have a habit of doing this. And it also kind of depends on the question you're asking. The big difference we're going to see between clinical and research is around that, what is enough evidence? What is the number and the thing that you need to know? And so we actually fall back a lot on precedent. And we do that in all the disciplines. What traditionally have people done to answer question X? And you use that research, that literature base that's already published to go, this is the method I'm going to use to try and prove whatever it is I'm going to try and prove. But precedent can be and should be challenged. See it in case law as well. there comes a point where technologies changes, methods changes, all these things cumulatively build up. So actually, sometimes by the time you get to your end of your PhD, the technique that was the centre of your PhD is no longer valid, or is still valid but is so far behind other technologies that have come in whilst you've been there that your data becomes unpublishable because you're now no longer using the valid. I'm not bitter. Not bitter at all, but it's what happened to me. So standardised methods do exist, and you have done some of them. Think back to micro in level 1 when you did growth curves. Yeah. So they are standard, they exist. They are the bedrock of microbiological research. Pretty much everyone, the first time they set into foot in a lab to do a microbiology project, will get to do a growth curve. They'll get to know and to understand the characteristics of their bug. Good news here, it's numerical. It'll either be mine, this is some experiments I did in my postdoc, where I was looking at the difference in Campylobacter grown in different conditions. So that it was in microaerobic, oxygen reduced, and then extremely oxygen reduced. So I was looking at the different concentrations of oxygens and the impact on growth. And I did them by the standard, nice, normal method. Set up a standard inoculum, put it into my broth. This is actually an N of 3, because if you try to do N of 9, doing 3 lots of 3, which is good, I'm sure the stats people are saying the more N you can get, the better power. And when you've looked at experimental design, you've got that internal reproducibility and then the external reproducibility across different days. Doesn't always work for bacteria, they're not that nice at behaving. So what's quite common in microbiology is to actually do an N equals 3 and look at the pattern. And if the pattern looks the same on different days, even if the number is slightly different, you'll accept the pattern rather than the absolute number. My data's not too bad, slightly clunky error bars on the 6th hour, but in general, the error bars are nice and tight, good reproducibility within. So, can do some stats on that. My sister would say this. Don't tell the previous lecturer I'm saying it as well. We become obsessed with stats. My sister would say, if this line is here and this line is here, why on earth do you want to do stats? It's obviously different. And my sister can say that with some validity because she's a statistician. What she does as her day job. But for you, you will need to do stats. There is a lot of stats in my PhD thesis that a statistician go, what on earth were you doing that for? But we have become used to it. So you look for the reproducibility and then you use the significance on the statistical analysis to say, yeah, it's significantly different. But yeah, you try. Then there's some other data, and we kind of almost touched on this earlier with the relative data. So here, this is DNA microarrays. Did Ian mention microarrays at all last week? Yeah. So this was a microarray that had every gene of the Campylobacter genome represented on it. I took my microaerobic and my highly oxygen-limited cultures, standardized for OD because they were very different, then extracted the mRNA out of them, and then merged them into a microarray for a competitive analysis to see which had more of which in. And this is the sort of data you get. And this is where this concept of using precedent comes in quite a lot. Here, if the nearer the dot is to the centre line, the closer it is to having equal amounts in the two samples. So you had the same amount of RNA of a particular gene in each sample. The outer lines represent a twofold difference, and in general, the precedent is But if it's greater than twofold difference, either way, then that is a significant change of ratio. Make sense? So you can see, particularly in this sample, it appears that lots and lots of genes were being transcribed at a lower rate in the oxygen-limited conditions. So when the organism was stressed, it was switching off some genes. Probably. Okay. But it's all relative ratios. I can't say categorically that these are definitely down-regulated. I have to be very careful how I interpret it. And I have to be careful not to oversell. But equally, I've got to be careful not to undersell. People like me get very cynical of some of this data. I mean, I've got a PhD in molecular microbiology, but I'm quite cynical about it a lot of the time, almost deliberately. I want somebody to prove to me that it works better than other methods. But when you dig a little bit deeper, actually, when you start putting filters on your data, and I put a filter on here for all the ribosomal RNA genes. So that's all that I wanted to show on the graph. And here you can see that with a couple of exceptions, they are all either low side of normal or very low, and are all going down. So you can start to infer pictures and you can start to infer ideas of what's going on. But actually, things like microarray and the next method we're going to see in a moment, they're basically fishing exercises, in my humble opinion. You are throwing out a scenario and getting back 3,000 results. By chance, you then might find something interesting. But you then have to prove it by biological experimentation. You can't absolutely categorically take microarray data of this nature to mean something. You would have to prove that it then has a biological effect. And this one, it starts to introduce a real issue that affects clinical labs. How do you prove a negative result? How do you prove the absence of something? You know, it's actually really much more difficult than trying to at least get strong evidence for a positive. So this is some 2D gel electrophoresis. Did Ian mention that last week at all?
Yeah,
No?
he did.
So having done my genomic analysis, I wanted to look and see whether that gene difference was doing anything at the proteomic level. Now, I've actually put up a different plot here. This isn't the ribosomes, but this is an enlargement of a 2D gel electrophoresis that a full gel will have. You can't see every spot, but it could have a couple of thousand spots on. Around 500, 2 to 500 of which will be usable. If they're very pale, you can't really use them. This technique for separating gels, separating proteins, is really quite basic. It's been around since the 1970s as a method. But it was the computer capacity for doing the analysis that means this really only took off as a method in the 2000s. You put in replicates, so each of these is a composite of 3 replicates of the 3 conditions. You also create a reference gel of all 9 to try and get a sense of where things are. And then the computer will do an alignment for you. Believe you me, you do not want to do it manually. It's really problem, but you then have to check that the computer's got it looking right. And so you can then see whether your reference dot is there on all your gels. So for this nice large, which I think memory serves as a flagellar protein, it's there on all the gels. It's nice and clear and evident, regardless of condition. Campylobacter still has its flagella. Fine, that wasn't the question I was asking. I was actually looking around the formate dehydrogenase gene because I was looking into the respiration of Campylobacter from the microaerophilic. And here what you can see is that you've got dots when it's under oxygen restricted, fainter dots when it's under middle oxygen, and as you can see from the bar chart on the side, the dot all but disappears. There's just the faintest hint of the dot there, which you probably even can't see. You have to rely on the fact there's a computer did that analysis and said, although you can barely see it by eye, there is something there. You have to trust your software a lot sometimes, which is another problem for me. But you can see it then converts it and uses a pixelation value, a spot density value to show that in the extremely oxygen limited, a lot more of this gene comes up, protein, comes up. At middle, it's increased but not as much, and at normal conditions, it's relatively low. And that's nice, but you still have to put that into biological relevance. Just the numbers don't mean anything. Fortunately, the logic says this is a sensible result, because formate dehydrogenase is used as part of an alternative metabolic pathway when there's low oxygen, so that the organisms can still grow. So it fits. But what if the spot's missing completely? How much confidence can you have that something hasn't gone wrong in your prep? It comes with experience, really. And there are loads of things that we do routinely in microbiology that we know have got faults with them. I've put one example up here, which is the gentamicin protection assay. Have any of you heard of gentamicin protection assay? So it's a way of looking to see if bacteria have gone intracellular. The theory is that if your organism goes intracellular, it then is behind your eukaryotic cell wall. Gentamicin, this is one of the weaknesses of the assay, usually at low concentrations for not too long an exposure, doesn't cross into eukaryotic cells. So if you incubate your bugs and your cells together, then wash them to remove any extraneous ones, then add gentamicin for a brief period of time, any exterior bacteria will get killed off, but the ones in the middle, because it doesn't get taken in, because the gentamicin doesn't get taken into the cell, will survive. If you then wash it to remove the gentamicin again, then lyse the cells, any bacteria you recover must have been unicellular because they were protected by the eukaryotic cell membrane. 55 journal articles between 2005 and 2015 used the gentamicin protection assay. Equally, a number of papers are out there saying this method is rubbish. This method has major issues with it. A, we now know gentamicin can cross the eukaryotic cell membrane if you leave it long enough or too high a concentration. It will get in eventually. But it's also basically recognised that it's the best thing we've got at the moment. So should we stop using it because it's got one or two faults with it? Or do we have to go with it till somebody invents a better method and then review our results? And that's the thing. Methods, techniques, precedent, they all change. Dave also mentioned to me that you had Andy Ridgway a little while back, and I checked with him what he said to you about the MMR. I put MMR event. My normal terminology is MMR debacle that affected this. And this was a piece of possibly the worst published science in living history. So a paper that in its title makes no reference to MMR or autism, had no controls and relied solely on parental recall, caused chaos. So when we take material and we overstate what it's showing, then we have the potential to really have a negative impact on the perception of science in the public domain. So it's important. That said, with the master's students, and I suspect with you, we actually tend to find that we're a bit too reticent to say things are true, and actually we sometimes need to sell things a bit harder. That's actually more common than overstating. More common. So make the best of your data in research, but don't oversell it. So that's the research setting. Any questions? We've not proved anything really, have we? We've just kind of said you make the best of what you can. And basically you do a lot of intra-comparison. You compare your results to your results. That's what a lot of microbiological research is. Comparing to others is always problematic. You have to do it as part of the review process to see if the material makes sense. But you can be stymied by things as simple as water coming from a different source. It can change your data really quite simply. So you really have to be careful. Now, those of you who've been out into the clinical labs a little bit will know that actually the clinical sector goes completely against the realms of good statistical evidence. How many repeats do you do? 1. N equals 1 on pretty much all clinical diagnostic microbiology. There are a couple of exceptions, but they're very rarely done these days. But essentially, you do a single assay result-based decision. Same is also true mainly in biochem and haematology. Unless the machine spits out an anomalous result, where you might retest it, in general, clinical diagnostics is done on a single reading.
For to cross blood type, always they do multiple.
Yeah, there will be exceptions, but in micro, it's almost always a single point reading. Almost always. Never say always, never say never, as we'll see at the end. So what do you do? Because you're doing this because it's a balance between practical necessity and cost-benefit analysis. What is the benefit of doing 3 readings? If you get a positive result, is there much benefit from a clinical perspective to doing 2 more than just saying the same thing? There are times where you might go, yes, but it's almost always 1 specimen, 1 set of tests, no replicas. So you control at the lab level. So the lab will be the bit that's controlled rather than each individual sample. You have strict standard operating procedures that must be followed in order to ensure that the sample is handled in a manner that best gives a chance of getting the most accurate answer. So if you're plating up samples, you'll start with the most nutritious media first. Say you've got a swab, you always go to something like a blood agar first. Then you might go to something like a pled. Then you'll go to the plates that have got antibiotics in. You don't ever go from the other direction. You go in a set order to minimise the cross-transfer of something that might inhibit growth. All your controls, all your assays, all your runs have to have controls in them. They have to be validated on a run-by-run basis. But for me, the real difficulty is proving the negative finding. We already said earlier today that methods change and get better over time. They get more sensitive. And actually, a lot of samples that maybe 15 years ago were sent out as negative for chlamydia might now test positive because the method is so much more sensitive. It doesn't really mean that the previous result was wrong, technically, but it does mean it was wrong biologically. For that patient, they did have chlamydia, but you weren't able to detect it at the time. And all assays in clinical labs have a limit of detection. And then there's the curse of the normal flora. Because there are plenty of infections in clinical sector where it's not the absence of an organism that's the problem. It's the change in ratio compared to the normal flora. Particularly for things like skin. If I've got a mixed culture with 1 colony of Staph aureus and 36,000 colonies of Staph epidermidis, that 1 colony of Staph aureus is probably not doing anything. But if the balance was the other way around, or even if the balance was 50% Staph aureus to 50% Staph epi, then it would change my interpretation. So the normal flora is a real pain. And we're going to see that, well, we've already seen it in SDOD with things like the fecal samples, and the fact you end up with plates that don't say what's causing this person's food poisoning. It says, is there any Campylobacter? Is there any Salmonella? Is there any E. coli 157? So it asks specific questions, not really, really general ones. So the way we do clinical microbiology is based on precedent. We know Salmonella, Shigella, Campylobacter cause food poisoning, so we look for them. We don't try and look at all the E. coli that's grown. If we did, we'd be there for days following up a single patient sample. And on balance, they probably don't have it. So, as I mentioned, you have these standard operating procedures. So the UK has millions of the things. Well, not millions, pushing 150. Every single sample has a set of an SOP to do with it that determines what plates go up as the minimum. So the SOPs are the minimum that laboratories are required to do for that given sample. They can do more, and some do, some don't. That decision may well be made based on local epidemiological knowledge. So if an area has a high incidence of an organism that isn't normally a priority one, then they may look for it more routinely. But they're a compromise. They really are a compromise. If we were to want to be the most sensitive method under the sun for a lot of things, we would be doing molecular biology a lot more than we do in clinical microlabs. You know, methods for detecting Campylobacter from fecal samples have existed for about 15 years for looking for them, for showing that they're there. We don't use them because the cost-benefit analysis is that it costs about, being generous, it costs as little as £3.50 to do a molecular test. It costs about 40 pence to do a plate, to just do a culture plate. And so clinical labs within these SOPs, there is a compromise over whether the extra cost is worth, whether the extra benefit of a more sensitive method is worth the much, much extra cost. And actually, there are people who say we should just scrap doing fecal microbiology full stop, because we so rarely treat, who cares anyway? So there's an element of real issue around the cost benefits, and all SOPs are a compromise. They are not perfect. They were written, they also go slightly out of date and have to be reviewed and renewed. But even now, I was reviewing one a couple of weeks ago, it has reference to molecular as a optional extra to the existence of the culture medium. So there's some real issues around how to control that. Quality control of diagnostic labs, then you have to be accredited. As I said, it's currently going through the switch to ISO 15189. But also clinical labs in microbiology are part of an external quality control system. So a central laboratory that is not linked directly to any of the clinical labs will set up fake samples with known pathogens in it. And they will then get sent round all the laboratories that are registered to do that type of sample around the country.
Is that the NEQUAS?
The NEQUAS scheme, yeah, NEQUAS. And all the labs will then test it. If they are doing it according to the letter of the guidance, you test it as if it was a sample that was coming in routinely. You do no extra testing. And most labs stick to that quite closely. Maybe one or two fudge it slightly and put up a couple of extra plates that they wouldn't do if it was a clinical sample that would just routinely come in. But in general, the labs do it to the normal standards. And then they have to report and send a report back to NEQUAS, who then will issue what the expected results were. And then the labs are scored. So if they get it exactly the same as NEQUAS said should be there, they'll get 2 out of 2. If they get it close but not quite right, they might get 1.5. If they get it completely wrong, they'll get a fail, and that will then trigger an internal audit, internal check of what went wrong. Why did they not get that result right? There are sometimes some anomalies, because labs sometimes, if they have a go at speciating and get it wrong, will score worse than labs that don't have a go at speciating and send it out as a genus level result. So they might only say Campylobacter species, and if they report that, they'll get 2 out of 2. If they have a go at speciating it and get it wrong, then they'll get a lower mark. Not as low as if they'd said no Campylobacter present, but they will get a penalty on their score chart. So again, that's linked to the SOPs. Labs don't have to speciate Campylobacter, so if you go above and beyond, that's a risk you take. Labs also run internal QC systems. So the most normal one is to pick a sample that's already been processed, write a fake request form, and resend the swab through the system for testing. It's not perfect, as we already mentioned. You would never go from something with antibiotics back to a plain plate, but you would have to if you're reprocessing the same sample. And of course, if there were only a very small number of organisms on the original swab, they may not come through on the retest. So it's not a perfect system. But in theory, at the end, the lab quality manager will take the two reports and compare them. They will compare for not just what the lab did, they'll also check things like the fact that the clerks entered the data, patient data accurately, and stuff like that, to check the whole process from receipt through to reporting. So it works. It works quite interesting. Some other labs, they will, the first person will read the bench, and then a second person will read 10% of the plates as a second pair of eyes. And hopefully they'll be in complete concordance. Occasionally they're not. And then you have to do an investigation onto which one of them is right and how did the other one get it wrong. So there can be other methods, but they're a little bit clunky. None of them are perfect. But sample audits. Also, as I mentioned, every assay will have to be controlled. If it's an ELISA or a PCR run, there will be controls on every assay run. And if your controls are wrong, you invalidate the entire test run. So you can't accept any of the data from that run. You have to rerun every sample. Bit of a problem if it was a very small sample and there's not enough to rerun. Then you have to grovel to the clinician and ask them to send a repeat sample. But it gets close. So how then are we proving that a patient's got an infection? I would proffer that at a sterile site, it's easier to prove a positive than it is at other sites of the body. So take cerebrospinal fluid, blood usually. I'd even almost make a case for urine in an otherwise healthy person that is passing urine regularly with no signs of infection. If you saw a CSF, if you saw a CSF and it looked like that, the patient's got no white cell response and they're dead. Because if they've got that many Neisseria meningitidis visible in the sample, then they are no longer with us. And of course there should be white cells there. But if you've got a CSF that should be sterile, you would be very worried with anything you saw. Anything. Because there shouldn't be anything there. You do have to allow for the technical competence of the person who took the sample, because they can be contaminated. But that would worry you. If you saw a urine sample in the UK in particular, but anywhere in the world, and you saw these beasts in there, you'd be pretty sure that the patient had a parasitic infection. They are never normal flora, and most of the time you wouldn't count your urine as having a normal flora anyway. Anybody know what that is? I showed you it briefly in ESPOD. This one's Trichuris trichuria. So it's a bladder parasite. That's fairly conclusive if you see it, but remember how long you were looking at those negatives for in ESPOD? So if you see a positive, it's reasonably conclusive. But if you don't see anything, how conclusive is it? For urine, if you get 1 or 2 colonies from 10 microlitres of urine, you probably won't think anything of it. If you get growth all the way over a culture plate, then you probably will, because it would suggest high numbers way above contamination. So you have to put it into the context of the sample that you're looking at. And you also have to bear in mind there are loads and loads and loads of exceptions to rules, including around urine microbiology, where for some patients, even without white cells, you'd still be worried about a 10 to the 3 count. So it's all context driven for individual patients' diagnosis. So yeah, I think I would be happy to say that for a sterile site, you can prove a positive fairly easily. But you can't prove a negative. If we go back to our CSF, the clinician may well have drawn off 10 mils. You don't look at or culture absolutely every bit of that sample. Again, think back to ESBOD when you were doing those fecal microbiology films. You did not look at every portion of the sample. So you can miss things just by testing luck, bad luck, good luck, whichever luck. And then, as I said, the curse of the normal flora and mixed cultures. How on earth do you interpret what's going on? If this is from you've got this complex normal flora, and so even from a site like a leg ulcer, interpreting what's going on with complex normal flora being present is really difficult. You've got mixed cultures of 5-6 different organisms. It's really hard to work out what might be going on. If this was from a catheter urine, probably, if you think back to Reg, probably wouldn't be that bothered. Catheter urines, mixed colonies, probably contamination. And if you had no white cells and no markers in haematology of an infection, probably wouldn't worry. Clinician probably wouldn't worry. But if you had really elevated white cells, then maybe you would be, because it might suggest it's moving from colonisation and contamination towards infection. So it's context dependent. This one is one of the ones we've also seen. So here we've got a fecal sample on a Salmonella Shigella selective agar, and there's a couple of colonies there that would raise triggers. But you can't test every single colony. What if they've got both the Proteus and the Shigella? We had that with Colin, didn't we? We had that he had a Shigella. No, he didn't have a Shigella. He had a Proteus. We were doing it, but you only tested one colony. What if by chance that one's a Shigella, but that one's a Proteus? There is elements. Sounds like you really shouldn't trust clinical labs at all, doesn't it? But actually, the evidence is that most of the time you're going to be right as to whether the patient does or doesn't have an infection. But not every time. And also, there are body sites where presence doesn't mean disease. So we've already touched on that. Proving choice of therapy. This sounds like it should at least be a bit more simple, a bit more straightforward, a bit more conclusive. Yeah, okay. So this is a culture plate of E. coli. It's from a urine sample. And those zone sizes checked against BSAC zone sizes. So that's how you do antibody testing. You test your organism and compare it to published breakpoints. So according to the zone sizes here, this is a fully sensitive organism. But sadly, the patient doesn't respond to the choice of antibiotic that the person chooses. The lab cannot prove what therapy is going to work, because there's so much that goes on in the human body once that antibiotic is put into them. They can recommend, and they can say, based on lab testing, these 6 antibiotics, any one of them should work. But there is then so much about the patient that can change that. And also, maybe not for urines, but for other body site infections, also the form that bacteria is growing in the patient. So in the lab, as you've done yourselves, this is all done on planktonic cultures, where the organism has loads of space, loads of nutrients, and grow really, really well. In the patient, it might be growing as a biofilm, or it might be located in a nutrient-deprived part of the body, and they're not getting everything they need to grow well. And so even if you can get the antibiotic there, it might not work in the phase that the organism is growing in. So those of you who've gone to infection science and microbiology, Shona Nelson would cover that a lot. The fact that organisms that are growing in their biofilm form are resistant to therapy and are a major healthcare problem. So there's lots of reasons. You can only, essentially the only proof that your therapeutic choice is going to work is when the patient recovers. Ultimately, it's guidance, it's a suggestion. And it's also why, if you think about it, how many of you have been to a GP, talked him through him or her through your symptoms, and then walked away with a prescription on the same day? Yeah, a few nods going around the room. Yeah, a few hands. They haven't got this. They haven't even got the guidance. They've gone on knowledge. They've gone on precedent. They've gone on what, in theory, is the most likely to work. Now, they may have taken a sample that they send to confirm it, but half the time they probably didn't even do that. More than half the time they probably didn't even do that. So, it'll guide, but it doesn't prove. And how on earth do you prove a negative? We'll come back to that question. I've put up a couple of examples here. Finding a clear pathogen present, kind of job done. You've shown a probable causative agent for the patient's problem. But how do you categorically prove a negative? Now, again, think back to Colin in the discussion we had. I made you go all mealy-mouthed and say, you don't say no pathogens present, you say no pathogens isolated. Subtle difference, but accurate. In the lab, you did not isolate it. Doesn't mean it wasn't there. It means hopefully it wasn't there, probably it wasn't there, but it might have been. So effectively you can't. We've already mentioned that testing methods get more sensitive, so things get wrinkled. We've already mentioned the don't test the entire sample. So these are a couple of examples. Let's do the bottom one first, because it does link back to Colin and all that 5 minutes each you spent looking at negative preparations. If you see something, it's fairly conclusive, but you can be going for several minutes. It's the same in cell path, particularly in cervical screening, where you have to look at each film for a minimum period of time before you can call it a no suspicious cells seen sample. So there is this difficulty that if you see a positive, it's straightforward. This is Mycobacterium tuberculosis, so a fairly important pathogen. Usually if a sample is going to go positive, it goes by around 3 to 4 weeks. But actually to have a better confidence in a negative result or a no TB isolated result, you'll actually leave the sample up for 8 to 12 weeks. Because if it hasn't grown by then, it's probably not going to. But you can put probably in that sentence. Because there will be exceptions where somebody left it up for 20 weeks and it did grow something. But you kind of can't inoculate and you can't culture things forever. You run out of space. And I said we'd just come back right at the end. Any questions on the proof in the diagnostic side? So right at the very end, we'd come back to epidemiology. And I did say earlier, we have some of the best epidemiological data in the world. The UK has some of the best, but it is still fundamentally flawed at numerous levels. So this is from a food poisoning lecture that those going on to level 3 will get in detail. But of the samples that get sent to the lab, maybe 1 in 20 yields a pathogen. The other 19 were probably negative. Of the people who had samples sent, for every one that a GP sent a sample to the lab, another 10 GPs probably said, go away, let it see if it resolves, come back in a few days if you're not better, and we might take a sample then. Being honest, do you go running to the GP every time you have diarrhea? In general, adults don't. They just deal with it. And then there's people who are infected but don't know they've got it. So for every fecal pathogen that I can think of, there is an underreporting. Some studies from Australia have shown that for every positive that they get in Australia, 14 other people were positive but were never confirmed. So essentially for our data for food poisoning, I recommend that you add a 0 to the end and you'll be closer. So our data says we have around 50,000 cases of Campylobacter in the UK per year. I would at least stick a 0 on the end and actually possibly times it by 14 rather than by 10 based on the data that's out there. So it's all underreported. We get other flaws. Mentioned earlier that the C. diff testing was initially only done on the over 65s. So it looked like it was a disease of the elderly. We now know that's not true. It can affect anyone. The only age group you don't worry about it in is the under 2s because they often carry it transiently normally and then they shed it. So we know things change, but data tends to be skewed towards children and the elderly because they are the groups that we perceive, probably quite rightly, to be more likely to have a negative outcome. So if you have food poisoning, you are likely to go, oh dear, I better eat bland foods, drink lots of fluid, hit the Lucozade, whatever, make sure my salt balance is alright, and I'll be fine in a couple of days. Parents tend to worry more about their children, and we also tend to worry more about the elderly because biologically both of them are more likely to have a negative outcome, particularly in the elderly if they've got anything wrong with their renal system that increases the probability that they're going to dehydrate. Add in the psychological aspect that the elderly are reticent to drink lots of fluid because they don't like to have to keep going to the loo. So there's actually evidence that a lot of elderly people live in a semi-dehydrated state anyway. So if they've then got food poisoning, they're more likely to tip over into a problem state of dehydration. So for many diseases, those notifications we talked about earlier, Campylobacter is a notifiable disease, but the data is underreported for them all. So, my take-home message on a very cynical day is, can we ever prove anything in clinical or research microbiology? I would say probably not. I think we can probably prove a diagnostic positive if we've got a patient. But even that's got one caveat to it, and that's the possibility of cross-contamination. If you've cross-contaminated from a positive sample to a negative sample, you can get false positives. They do exist, particularly in molecular testing systems that are very, very sensitive. You only need a transfer of a very small amount of nucleic acid over, and it will contaminate your future samples. And so, those of you who go on to microbiology will hear me say it a lot. Never say never or always. Really bad ideas. Okay? And I suspect you'll find everybody else says something similar eventually. But you're at the stage now where you can cope with it. Cope with uncertainty.
What do you mean?